Hello students, welcome back. So now we are going to be focusing on gradient descent. So this gradient descent, it's an iterative optimization algorithm. And what it does, it is used to find the minimum of a function. So in your machine learning model, this function is called a loss function. Another name for that is a cost function. And what this function does, it measures this loss function, it measures how wrong your model predictions are. In other words, it kind of like tries to find out the difference between your actual value and your predicted value from your machine learning model. Now, this particular gradient descent method is well suited for large data set. So suppose we plot the cost function versus the parameter, and let's say it comes out to be something like this. This is the shape. So in this particular case, you can see that the minimum is over here. So what you're trying to do is you're trying to find this parameter right here. At what is this point where your cost function becomes minimum? Now, in machine learning model, you will find there will be always be some difference between your actual numerical value and your predicted numerical value. For example, let's say you create a machine learning model that takes the age and weight as an input and it makes a prediction. So this is my prediction, and let's say the actual value is these. You can see that the actual value for this data is 3 and the predicted value is 5. The actual value is 1 and the predicted value from the machine learning model is 2. And likewise for 7 is your actual and your predicted is 6 right here. So in this case, you can see that there is some difference between your actual and predicted value. So the goal of gradient descent, it is to adjust these model parameters so that this loss, it becomes as small as possible. In other words, you are trying to find this parameter that would make the cost function minimum. If you recall, in your linear regression, the cost function was given by this expression right here. This MSE stands for mean squared error. So basically, you're taking the squared difference between the actual and the predicted value, and you're squaring everything, and then you're dividing by the total number of data points. In this particular instance, your y, which is your predicted value, is given by this expression right here. So your b plus m times of xi. So this is your predicted value. So here we have to find this parameter m and b so that this function, this cost function, is minimum. So suppose we start with some parameter, say b, and then we keep changing it by a constant amount until we find the minima. So for example, let's say we have a b equal to 5. I start with my b equal to 5. So this is my b equal to 5 over here. And let's say my cost is this right here. Then I decrease my b by 1. So now my b becomes 4. So this is my cost right here. All right. Then I decrease my b by 1 again. And then my b becomes 3. And let's say this is the cost function. So you can see that as your 5, as your b is decreasing from 5, 4, 3 to 1, your cost is decreasing. But it is also possible that when it reaches over here, it may overshoot your minima. Your minima is over here and it just overshoot. It just went over that. Okay, it kind of missed it. So that is a problem when you are decreasing your b by a fixed amount. It may overshoot the minima. So the solution is this, that we change the parameter not by a fixed value, but by a variable rate that depends on the slope. Now, this rate has a special name. It's called learning rate. So suppose this is my C right here for the linear regression. So in this case, the slope of C is given by, when you differentiate that with respect to M, this would be your slope of C with respect to M. And this would be the slope of C with respect to B. I'm assuming that you know derivative, partial differentiation. If you do not know partial derivative, it's okay. Just assume that this is basically done for you by the mathematicians. So we find m and b by repetitively updating its value that depends on the learning rate and the slope, and then calculating the cost function. And we keep doing this process until we find the value of m and b where your cost is minimum. So now my m is going to get updated like this. Your m is going to be equal to m, which is your previous value, minus this called a learning rate, times the slope. This is the slope I just showed you. Same thing with your b. Your b now becomes equal to b, that will be your previous value of b, minus eta. This is eta, by the way. This is a learning rate, times del c over del b. This would be your slope of c with respect to b. So with the introduction of this learning rate, what happens is this: as you're decreasing your value of b. Let's say we're only focusing on b. So as you're decreasing your value of b, let's say your b1 was your start value, your b2 will become equal to previous value of b minus eta del c by del b. So your b2 becomes this value, your b3 becomes this value, and you can see that your b2, b3, b4, b5, as they come closer and closer, they become very smaller and smaller. So the this step going from here to here to here to here, these step size, they become very small, and this way it would not overshoot your minima. So this is a short summary of the algorithm. You start with initializing your parameters. Another word for that is weights randomly. You pick up your values m and b randomly. Then you compute your loss using your current parameters. In other words, you calculate the difference between the actual value and the predicted value. That's what your loss is. Then you compute your gradient. Gradient would be this value right here, this one. So this is a gradient with respect to b right here. This is the gradient with respect to m. You compute that. And then you update your parameters. You update that using this rule for m, and you update b using this rule for b. And then you keep repeating this process until you reach a point where your cost function is no longer decreasing. In other words, when you reach a convergence. So now I'll show you how you can implement the gradient descent in Python. That's easy. First thing you do is import your numpy as np. And this is my function right here. In this case, in this function, I'll pass my x and I'll also pass the value of y. This is the one that's the actual, that's the target. Okay, so in this case, you start with m equal to 0 by b equal to 0. I'm randomly putting some numbers over here. You could put any other number. Then I specify my learning rate. So I start with learning rate as zero point 0.1. So later on, you can change this to 0.01, 0.05. And by the way, this is a hyperparameter. That's the technical name for that. Okay, then I'm also determining my length of my records. In this case, it's n. Then I'm just iterating. I'm gonna do this thing at least 1,000 times. So that's what I'm doing over here. So in the first iteration, I'm making a prediction of my y value. So my y is gonna be equal to your b, that the one you just chose over here, b plus m times x. And here we have to find b and m. That's what we're going to be trying to do in this loop over here. Okay, so it makes a prediction right here. So then I determine the cost. I actually compare my y actual with the predicted value. See how different they are. Then I square them, and then I add them all together, and then I divide by n. That's what I'm doing over here. I'm dividing by n. So this gives me my mean squared error for the linear regression, by the way. So then I'm printing my I. This I is my iterator right here. I'm also printing the value of m, b, and cost function. By the way, I'm rounding them off so that I don't see all the bunch of crazy decimals. Okay, then I find my m derivative. So if you recall, the formula for derivative is basically this, right? A minus 2 over n multiplied by sum. You basically are you are subtracting y from the y predicted, and then you multiply by x, and then you multiply this thing. You basically add them all together, then you do 2 divided by n. So over here, what's happening is this. Essentially, I'm calculating this value right here. That's what that expression was doing. And likewise, the other expression, that's calculating this, right? So this one right here, b plus m times xi, this is your predicted value. Okay, coming back to this. So I calculated this right here. This is what this one does. And likewise, I'm calculating the b derivative. That's my answer. And then I update my value of m. So the way you update the value of m is you say m minus learning rate times m derivative. That is the same thing as updating this value right here, m and b. So we updated m by saying m equal to your previous value of m minus the learning rate multiplied by your gradient. And same thing with your b right here. And this is exactly what's happening over here. I'm multiplying m, this is my previous value of m, minus learning rate times m derivative. Okay, so this is my function right here. And I call this function 1,000 times. And then I define my x and y. So let's say my x is equal to 1, 2, 3, 4, 5, and let's say y equal to 5, 30, 20, 40, 60. This is my actual predicted value of my y. So let's run this function, gradient descent. And when I run this, you can see that it gives me these values. These are my m. So the first one was, let's see, m and b, and then cost. So my m is this right here, my b is this, and look at my cost, and look at these costs. Look at that. Oh, cost is just kept increasing, kept increasing. So this is a scenario where basically you overshoot that. Okay, your learning rate was too high in this case. Okay, look at this value, very big, very large values, and look at this thing. All right, so this is not working out. So what I'm going to do is I'm going to change the learning rate. Let's change it from zero point 0.1 to 0.01. Let's see what that does. Let's run this and come back over here, run this, come back down, and look at this. Okay, now we are going somewhere. you have 10.19. So let's scroll down all the way bottom and let's see what exactly it's giving me. So yeah, okay, so see it reaches 56.1. So this is your loss function right here, and then it is pretty much like reached same, like it is just going 56.06. Okay, so that's good. So yeah, it seems like let me just come down. Oh yeah, there you go. Okay, so you can see that when my m is equal to 11.93, okay, and let's see, when my m, is that what the value is? Yes, my first value is m, the second value is b. So when my m is 11.93 and my b value when it's minus 4.74, your loss is 56.04. So it seems like up to here, up to 1000 iteration, this seems to be a good value. And you can see your cost function. You see it's not actually oscillating, it's just low value, it's not going below that. All right, so it seems like by choosing my learning rate as 0.01 and maybe iteration as 1000. By the way, go around and change, let's change the iteration number. In this case I just picked up 1000. Maybe you can make it to 100. Let's see what that gives. So come back down here, let's run this. I'm just doing 100 iteration, and you can see that in 100 iteration you got 61.56, 61.6. Okay, so it did not reach the 56. The actual value was 56 through the traditional method. It did not reach 56 because we only did 100 iteration. So by increasing the number of iteration, you can actually get a more better result. So by increasing the iteration and also by decreasing your learning rate, you get a better result.